Next is acceleration due to gravity and factors affecting it. We have discussed the Newton's law of gravitation, that is force acting between the two mass bodies is G m1 m2 oblique r square. And if we take the earth as one of the body and another is at the surface of earth, the total mass of earth is m, which is concentrated at the center. Radius of earth is capital R and mass body at the surface of earth is small m. Then gravitational force of attraction will be G capital M into m by capital R square. And this force of attraction will be equal to weight of the body. This implies that acceleration due to gravity is gm oblique r square. This is at the surface of earth and its value is calculated as 9.8 meter per second square approximately. This gravitational action is not a universal constant. It changes from place to place and due to various factors. We will discuss the factors and their effect on the acceleration due to gravity. First, G at a height h from surface of earth. If we go above the surface of earth, the effect of height on the G is that acceleration due to gravity decreases. This we can show here. This is the earth. This is radius of earth and from this there is a height h where a body is situated. This h is suppose very less than capital R. It is nearer to the earth's surface. Newton's law of gravitation, that is F equal to G mass of earth, mass of body oblique. Now what is the distance between them? This distance is R plus H. Total distance will be, here total mass m is concentrated at the center of earth and distance between small n and capital M is R plus H. So this is the final distance between these two mass bodies. So it is R plus H whole square. It is equal to mg dash. Now because g will be different, so we are using the g dash for the acceleration due to gravity at a height. It will be g capital M small m by r plus h whole square, and this small m will be cancelled. That means g dash will be equal to g m oblique r plus h whole square. We can also write it as gm oblique. Now we divide by r square and multiply by r square. It does not affect the value of g dash and r plus h whole square. This value we know from the above question number 1. It is g, that is the acceleration due to gravity at the surface of earth, into r square oblique r plus h whole square. It is equal to g. This r square, this numerator and this is the denominator, can be divided by r square. So we will get, in numerator I will get 1 and in denominator I will get r plus h whole square by r square. And if we take this r square inside, then we will get, this is 1 by 1 plus h by r whole square. It can be written as, if we take this denominator in the numerator, we can write it as 1 plus h by r raised to the power minus 2. And opening the theorem, we will get g 1 plus, this is the form of 1 plus x raised to the power n. It is 1 plus nx plus n into n minus 1 by factorial 2 x square plus and so on. So using this formula, we will get 1 plus minus 2 h by r plus minus 2 minus 3 by factorial 2 h oblique r whole square plus and so on. it is equal to, if we take h very very less than r, then h by r will be smaller, h by r is h square by r square will be more smaller, and other higher terms will be negligible. That means we take only these two terms and neglect all other higher terms. We get approximate value is g 1 minus 2h by r. Therefore, at a height h from the surface of earth, acceleration due to gravity will be g1 minus 2h by r, where h is very very less than r. This is the condition for which this formula is applicable. Otherwise, we have to use this formula if there is no restriction on the h. Next, we take acceleration due to gravity at the depth from the surface of earth. G dash at a depth from surface of earth. Suppose this is the earth, the center where m mass is placed, and there is a small m which is at a depth d from the surface of earth. Radius of earth is r, so this is, if we write it is r, that means r equal to r minus d. For such case, because it is a solid sphere, earth can be treated as a solid sphere, and for solid sphere, for the solid sphere, gravitational field at a distance r from the center will be E equal to gm oblique r cube into r, or we can write it is gm oblique r cube into r minus d. This formula we will discuss and will derive in the topic gravitational field. Here we are using it. So gravitational force will be F, that is equal to mass of the body on which gravitational force is applied, and gravitational field at the point where mass m is placed, and this is equal to the actually the weight of the body at that point. This implies that m into, and this is the gravitational field which is created by the this earth as a solid sphere at the point where m is placed at the distance r. So it is we are using this formula. It will be gm oblique r cube into r minus d, and it is equal to mg dash. So m and m will be cancelled out. This implies that g dash is equal to gm oblique r cube into r minus d, or we can write it as gm oblique r square. If we take one r inside, it will be r minus d by r, or we can write g dash equal to gm oblique r square into 1 minus d by r. This is g, that is the acceleration due to gravity at the surface of the earth. So g dash will be at a depth d from the surface, it is g into 1 minus d by r. Here again, gravity reduces as we go down inside the surface of earth, similar to the when go over the surface of the earth. Third is effect of rotation of earth.